Welcome to this demonstration of ModelVision using 3D visualization of magnetic vector components. We'll create BX, BY, BZ vector components from total magnetic intensity grid using FFT processing. We'll then resample that onto the flight lines, visualize them as vector, and then we'll validate using some synthetic models. To illustrate the method of showing the depth to a target using 3D vectors of the magnetic components, we'll start with a theoretical model where we know what the answers are and we can show how the 3D vectors will intersect either at the top of the body or inside the body. And where you've got very large variation in depth, this can be a helpful starting point to understanding the geology without having to first do the modelling. In the map view here, we've got 5 different body types: a tabular body, a sphere, that's a circular pipe, a sphere, ellipse, an elliptical pipe here. I'll illustrate those in 3D, showing the different body types. We're going to do the calculation through forward modelling and compute the components. Now we do that through the model line control menu. We're computing this along the flight lines. So we've got model magnetics on, and we go to the components button and we compute BX, BY and BZ. You would normally set the modelling component to BZ if you were doing inversion. In this case we won't be opening up cross sections. Click on OK, click on OK. We then do the forward computation for that model across all lines. I've previously made them active by selecting all the flight lines. Click on compute, it's reasonably fast. And then we want to turn on the vector display. And here I'm showing the vertical component where positive is to the right, negative to the left. And we see that we've got a negative vertical component of the magnetic field over each of these bodies. Now we can turn the profile vectors on in the map view, but it's not normally as helpful as it is in 3D. So I'll turn off the stack profile and turn on the profile vectors. And they're color modulated. We'll turn off the flight line. And we can see they're pointing towards the body. We've got different scales present, but they're basically pointing into the direction of the body. Because it's the southern hemisphere, I've inverted the sense of the vector by using a -1 multiplier. Now we can do the same vector display in 3D. Close this down. Where we've got the 3 bodies here, I've made them transparent. I've got the vectors superimposed on them. And to give you a good sense of how the bodies relate to the vectors, by rotating it, you can see how they intersect. For the sphere and the ellipsoid, they're very close to the top. For the elliptical pipe, which is this one, slightly below the top of the pipe. For the tabular body, some are inside the pipe, some intersect near the top of the pipe. But in each case, it's very closely related to the tops of the body below the flight lines. This porphyry copper gold system will demonstrate the application of the FFT filter to the total field grids to generate BX, BY, BZ grids. We'll resample those onto the flight lines, and then we'll visualize the component as vectors and finally compare them with the modeling results. In this example, we're going to show the method of 3D component vector display on a potential porphyry copper gold system in New South Wales. The magnetic data from the survey is part of a larger survey, but the primary anomaly complex of interest is this one. There are some young Jurassic volcanics superimposed over the top of the anomaly and some deeper basement features running through the survey area. Survey flight lines, we'll turn them on, show where they are located. And the first stage is that we need to compute the BX, the BY and the BZ components for this grid and then resample it onto the flight lines to produce the underlying vector components. So the first step is to process the grid using the Fft Grid Filters. And we're going to process the leveled magnetic data. This requires the use of the component vector display, the XYZ magnetic components. And if these BX, BY and BZ are ticked, a grid will be produced from the total magnetic intensity for each one. We can choose which preview we want to use. In this case we use BZ, it's Southern Hemisphere data. So the primary normal anomalies will look negative in this context. To run the FFT process, we click Save As and just click Save. We'll run through the process. It doesn't take long, it's a relatively small grid. And we'll close. It will then open the grid of data for the BX, the BY and the BZ components. So the next process, we now have the grid sitting in memory. We use the resample from grid. We can select all the lines. We want to sample the grids onto all the lines. And we would name the output channel BZ, the same as the grid. Now I've already done this computation, so I won't repeat it, but when we click OK, it will produce a BZ channel. We then do it for BY and then for BX, and we will end up with line data with the addition of the BX, BY and BZ components. Show them here, they've been pre-computed, BZ, BY, BX. This gives the range of the data. So we now have flight line data with BX and BY and BZ components that have been derived from the FFT grids. They weren't measured, of course. Now we can display those first in a map view, and I'll bring up a grayscale map because I want to display these in colour, and they don't look particularly good with colour on colour. So I've set this up in advance. We have the profile vectors, we'll turn those on. Now we see a little bit of data, but it's not particularly interpretable in a geological sense in a map view. We can see convergence of lines, but it's difficult to get any sense of depth. We have a very strong magnetic anomaly in this vicinity, and we can see the vectors pointing into this location. We have another one here which is very shallow. We have a few blue ones here, particularly where we've got reversed magnetisation. Close that down. The best way to display this data is in 3D. And here I've got the vectors displayed where the very intensely magnetised anomaly has quite long vectors displayed here. I'll rotate it so that it's looking north, so that those vectors relate to this magnetic anomaly complex here. But we have some much deeper, and you can see that one is quite shallow. The intersecting vectors are relatively close to the surface. But this broad one, which we would expect has longer wavelengths, much, much deeper. And another one out to the side here, which is part of the complex, is also pointing to similar depths. So immediately we're getting a sense of the depth of the magnetic sources without having to do any modelling. And it can be useful as a guide for separating visually. It doesn't work for all projects, but it's a useful starting point and something that could be done very quickly at the beginning of a project to get a sense of relative depth. So once we'd finished this particular project, we had a set of models that we could then compare with the vector display. I'm going to add those models into the display, add the bodies in, and I'm going to modulate them by property. And this shows them in solid mode. to modelling. This anomaly here corresponds to the orange model here. This deeper seated one corresponds to this broad anomaly. And the intense long vectors correspond to this anomaly complex here. So that modelling took some time to compute because a lot of interaction. Some are eminently magnetised, some are near surface. And by modelling all as a complete 3D problem, we're able to get accurate depths. We can see that the depths for most of these are matching in the vicinity of what we got from the modelling exercise. So as a starting point for modelling is a useful tool to add to our range of tools. So next time you have a total magnetic intensity image with a range of anomalies, give the 3D vector display a try.